Don, take it away.
Does that mean I was supposed to start, Wendy?
Yeah, here we go, was your cue.
Oh, okay. All right. Yeah, Wendy really likes it when you raise your hand, because then she can be like Roz on the old Frasier show and say, Don, Charlie in Columbus has a question. Well, welcome everyone. And before we start this brown bag session, which is number 10 for us on design previews, I just want to mention, I'll probably mention it at the end also, that I'm running out of ideas. So please, if you have ideas for brown bag sessions, don't hesitate to email them to either Wendy at Tec-Ease.com or to Don, or through requests. We'll get it any of those ways. So this brown bag is going to go for roughly an hour. I think the formal presentation will end a little bit before that, and hopefully there will be some discussion or questions at the end. Over the years, I've been into many companies, and they all seem to do these drawing reviews where they send a drawing around that's all dimensioned and toleranced, and they ask production and quality and suppliers, what do you think? And they come back with their comments, and the designer, you know, if you criticize the drawing, it's sort of like going up to a woman with a newborn and saying, man, what an ugly baby. You know, so often design doesn't take the review very well. And they're also reluctant to make the changes. They put effort into it, they put time into it, and so they're often reluctant to make the changes. So I have found over the years that design previews work much better. So that's what we're here to talk about. And to do a preview, we do it before the drawing looks like this one with all those darn boxes on it, the datum features called out, and the geometric tolerances. Now, if we think about this drawing, it is a common thread. It's shared by many areas. It is generated by design. They create it. It's their output. Therefore, they're the supplier, and they need to think about their customers. Now, their customer is whoever receives the drawing. And, of course, one that will always receive that drawing is production. So we have to make sure that what goes on the drawing is producible. Someone else who receives this is the quality or inspection area, because usually parts get inspected. So we have to make sure that what we put up here is understandable and inspectable, so they can inspect the parts. I just went through it, I won't name companies, but I just went through it with one company where they just cannot agree on how to inspect a particular call-up. And the call-up could have been made a lot clearer on the drawing. So we want to get this team together for a preview. We want to rally around the print before all the geometric controls and datum features have been identified. And so that's what I'd like to talk about in this brown bag. Many of you, I'm sure, have various types of phases and gates that you go through. And I'll just put one up here, one sample. And when we want to come up with a new product, first we want to gather the voice of the customer, make sure the customer is going to get what they want. Now, before we move on to the next step, we want to make sure that we have a clear understanding of what the customer wants. So you have to pay that token before you can go through this gate. So we have a guard here to make sure that you do that. Then we start to think about design alternatives, and that's where the designers and design engineers have those flashes of inspiration, you know, some solution to the problem to satisfy the voice of the customer. And so in doing that, we think about how we're going to build this product, whatever it might be, and we decide that it might be maybe out of sheet metal or a casting or a molded plastic part or a machine part. And all of these processes give us different effects. We get burrs and flash and parting lines and ejector pin marks and so on. So we need to think about those process effects. And I find very often people don't think enough about them. They have a prototype made in the model shop, and it might have been machined, but the part's eventually going to be molded. So they kind of miss that they're going to have to deal with draft and parting line and flash. And then at some point we have to assign specs and tolerances, and so often someone will email me and they'll say, well, what should the tolerance be? And I have to respond, well, what's the process? What do you think you can hold? What do you think you need? So I want to talk quite a bit about that during this brown bag. In order to do a good job on assigning the specs and tolerances, we need to know what the process variation is. And there's a couple of ways of getting that. One is when you have your design preview, you invite in the folks that are going to be making the parts, and they have a pretty good sense of what their processes can do. But another way is to look at the data. Many companies gather data. So if we have that data in a database that we can look up, then we know what kind of sigmas, standard deviations, what kind of variation to expect based on what we've done in the past on similar parts of similar complexity and similar materials in that particular process. You know, I often get the comment, well, we haven't made the part yet, so we don't know how good we can be. Yeah, but you've made other molded parts or cast parts, and they were similar, so you do have an idea. I remember Xerox used to have these pumpkin books, and in their they were called pumpkin books because they were orange. But in their pumpkin books, they would put several sample parts, and they would, in those books, tell people, here's what we could hold for tolerances on particular dimensions. We're a little more sophisticated these days, I believe, because we can look at CPs and CPKs, and hopefully everybody's heard these terms kicked around. Some of you probably know them very well. I'm going to spend just a few minutes giving kind of layman's definitions of CPs and CPKs and explain why they're so important, because they allow us to evaluate our design, evaluate those tolerances that we put on there by comparing them to the process variation. Many companies have CPKs that they're shooting for, 133, 138, 1.5. And so we want to ask a question here at the end: do the predicted CPK values meet the corporate goals? And when they do, oh, we did our job and it's time to party, everybody's happy, looks like things are going to be good. But sometimes the answer is no, these CPKs aren't what we hoped they would be. Well, if that's the case, that means it's time for us to go back and try and come up with a new flash of inspiration here that's better than the last one. So I want to just kind of talk a little bit about all of this. When do we conduct our design previews? Well, right in this area, when we're considering those process effects and we're looking at those specs and tolerances, and we have some design alternative that we think will work. We may want to modify that. Near the end of this brown bag, I'm going to take you through a case study on a fuel valve. So we get the team together. It should be a multifunctional team. That doesn't mean designers and engineers. It means get together the folks that are going to be dealing with the drawing, dealing with the parts, so production, quality, and so on. And what we want to do is define the ideal geometry. But it's not just the ideal geometry that'll function. It's the ideal geometry for material handling, for the manufacturing process. There's a lot of things that can drive getting the right shape. And also adding some features that may have nothing to do with the function. I have found that our competition overseas is pretty good sometimes at adding detail, adding features that help with the handling of the parts or help with the production of the parts. And I'll show you an example of that. Then we want to apply critical and producible tolerances where needed. Well, if we don't have an idea what our processes can do, it's hard to know what tolerances are appropriate. So we'll take a look at that. And then maximize our production tolerances without sacrificing quality and reliability. In other words, come up with a robust design. Often people will hear, oh, that new jig board that we got can hold 2 10,000ths of an inch. And they'll put 2 10,000ths of an inch everywhere. Well, just because it can hold that tolerance sometimes doesn't mean that we should put it on everything, because then that will become a big bottleneck. If I can open up tolerances, maybe I can create a lot of the part or all of the part on a less expensive process. Many times we were able to make our design more robust and go from a machine casting to using a die casting as cast and not have to machine it. I was a co-author of an article that appeared in Machine Design magazine back in 2005, March of 2005, And I co-authored it with a couple of friends from the United Kingdom, Marty Raines and Ken Swift, who have put together a product called Tolerance Capability Expert, and it's a database of process variation. And they've covered just about every process out there, and you can look up what you can expect to hold. So in that article, we talked about an actual fuel valve, and here's a couple of variations of part of that fuel valve that you see, and I'll show you more detail on that as we go through this brown bag. So much of what I'm going to talk about is drawn from this article. At that time, we coined the term process capable tolerancing. So you can look this article up on our website if you'd like. So we have this thing called PCT, which is a methodology for design previews, really. Process capable tolerancing. Where do tolerances come from at your facility? You might ask yourself that. There's a lot of answers. Past practices and carryover, legacy, I see that all the time. I was with one company, they were working on fuel systems, and I went back through their earlier designs. I was there in the 1980s. I went back and looked at some of their designs from the 1950s, and the only difference was they converted the inch tolerances to metric tolerances. It was just carryover, carryover, carryover. And so the problems that were created back in the 50s were continuing into the 1980s. So legacy, you see a lot of carryover. Data found in handbooks, going to Machinery's Handbook and other handbooks. But if you look at a lot of that data, it's based on poor quality. It's based on something like 3 standard deviations, 3 sigma quality. If you look in a Machinery's Handbook for the tolerance they recommend for drilling, if you want to do that at a 6 sigma quality level, you're going to have to ream those holes. So be real careful of that data that you find in handbooks. Seat of the pants guesses. I find a lot of people do that. In fact, I wanted Wendy to animate this little guy, maybe have this hand reach up here and show up with a tolerance. That's probably politically not correct, so maybe we shouldn't do that. Individual experience of the designer. When I first started out, I was working with these designers who had spent a couple of years in the shop before they moved into design. And they would say, well, on a mill, I could hold this tolerance. And maybe they could, and maybe they couldn't. But that often drove the tolerances we put on the drawings that got us into trouble a little bit later. Spec heaven. A lot of people say, yeah, where'd that come from? I pulled that out of spec heaven. I don't know. I look at some of the tolerances on drawings, and I'm telling you, they didn't come from spec heaven. Yeah, you might guess what's coming next. Yeah, they came right from there, and it wasn't heaven. So often we just tighten tolerances because when you do things on your CAD system, they're perfect, and they work in CAD. They always work in CAD. And we find that sometimes they don't work when we actually get into production. So one change you will see is tightening the tolerance. The closer your tolerances get to perfect, the more like that CAD model that did work. So what about function? I get this all the time. Well, tolerances are determined by function. I don't believe that to be true. I hear it a lot. But function doesn't determine the tolerances. Function is what the customer wants. It's how they want the product to perform. There are always design alternatives to satisfy what the customer wants. You never reach optimum. There are always alternatives. And some of those alternatives are more robust than others. Now, robust means insensitive to variation in the factory and in the hands of the customer. So tolerances are really determined by design alternatives that we select. And once again, I'll give you some examples of that. You know, the predicted cost of a product is determined to a large degree by the process that you pick and the materials that are used to produce that part. So they should be the determining factor when you're talking about tolerances and tolerance allocation. Now, designers need a way to know what the tolerances are out there that are reasonable. One way is to bring in the people that are going to make the parts. The other way is to gather data. Let me talk to you for just a few minutes about robust design. I've got a pretty good example here of a lack of robustness that I'd like to share with you. I don't know what kind of shoppers you all are. I'm kind of a hunter usually. I know what I want in the grocery store. I go in there, I get it, I grab it, I'm out of there. Except when I go to those home improvement stores, Lowe's and Home Depot. When I go to those, I'm more of a grazer. You know, I kind of graze around to see what's new in tools and so forth. And one time when I was grazing in one of these stores, I noticed this screwdriver hanging there, $2.69. And as I took a closer look at it, I see it was meant to drive slotted screws. But if you look real close here, you'll see there's a couple of tangs, and those little tangs should be up here in the handle. And if you really look closely at what they put in the handle, it's that flat blade that drives slotted screws. So this screwdriver won't drive any slotted screws. I found it kind of amusing that the company that made this had a slogan, "We want to help you do things right." So I took this screwdriver and I had to have it. The $2.69 was not an issue. I checked it out, and I took photographs of it, and I made some suggestions to the company. I said, short term, you probably should put a vision system on your line. It'll detect this through pattern recognition, and you can kick it off the line. Now that's detection, it's not prevention, but it's a short-term fix. To prevent this from ever happening again, I know they cold formed the tangs and they cold formed that blade. Well, since they're hitting both ends of the shaft, my suggestion was to cold form that flat blade on both ends. Then this is a more symmetric part. It's called alpha symmetry in a design for assembly course. You see, I know they can get the flat blade into the handle without even trying. And that would make it more robust in the factory. You'd never have this problem again. It would just go away, and that's prevention. Also, it'd be more robust in the hands of the customer. I've had some screwdrivers where these little tangs weren't big enough, and when you put the vice grips on the handle to turn a real stubborn screw, you can actually remount the inside of the handle. Well, with this flat blade here, this will transmit more torque. So I wrote to them making these suggestions to come up with a more robust design, thinking they'd send back a, I don't know, set of screwdrivers, maybe a whole toolbox full of tools. Who knew? Well, they sent me back a letter. They apologized for my inconvenience. They did send me this screwdriver that would drive slotted screws. Now, it might be that I angered them a little bit. I used their slogan against them. At the end of the letter, I said, "I'm telling you all this because I want to help you do things right." Probably shouldn't have said that. But the idea of robustness, insensitive to variation in the factory and in the hands of the customer. Well, in order to know whether you're robust or not, you need to look at the tolerances, and you need to look at CPs and CPKs. So we want to gather our team, depending on your culture and the product you're dealing with, and geographic issues. They're spread all around the world. I hear that. Our team involves some people in China and we can't get them over here. Well, sometimes you can do web meetings and that sort of thing. But what we want definitely is design in the meeting, and quality needs to be there, and inspection, and production. If you have something called supplier quality assurance, we want those folks to be there if possible, and of course suppliers of various parts should attend. And there may be others. Management sometimes, that's always helpful if management shows up for some of these. Purchasing likes to be there, so you may have some other folks you'd like to add to this list. You see, I have found a lot of companies gather a lot of data out there on the shop floor or at their suppliers about their processes. And I ask them, what do you do with that data? And they say, oh, we put it in a chart. We put it up on the wall. It looks really good when we have a tour come through. And they use it for process control. I'll give them that. But when I ask, do you put this into a database? See, if you take this data and you put it into a database that people can access, you create knowledge for your company, knowledge about the processes. And so if there's a database there that design can access to see just how good the processes are, they can use that to guide them in assigning their tolerances. Very, very effective. There are some software packages out there that have a lot of process data in them. I'll show you some results of one. It's called Tolerance Capability Expert, but there are others. And I really recommend that you build your own and keep it evergreen because processes change over the time. So what if you just ask the suppliers, well, how good are you? What can you hold? Well, they want the job usually, so the answer is usually some clown will say, hey, we can do anything. You know, we're the supplier. And what I really want to know is, okay, maybe you can do some things sometimes, but I want to know how good you are, how often. And that's where those CP and CPK indices come in. In other words, in God we trust, but all others bring data and give me the CPs, and especially the CPKs. But once again, I get that argument, oh, we haven't made that part yet, so we can't tell you how good we'll be. Well, you've made similar parts. Or another one I get is, look, we're only going to make a couple of these parts. We're not a Ford Motor Company. We're not going to make tens of thousands of parts. And so we really can't tell you the CPs and CPKs, the process capability. Well, I don't buy that one either. Back at the college, I had these slaves, servants, wait a minute, I'll get it right, students. I had students available to gather data for me. And we had 2 machine shops at the college. And so we would look at our machine tools out there, and some were donated and kind of old, old engine lathe, but it had a certain capability. And we only made onesies, twosies on this machine. But what we did do day in and day out on that lathe was produce hard round things, hard round parts. And when we did that, we knew what the goal was. We knew what we were trying to hold here for a size and here for a size. So within certain ranges, we'd say, how well did you do at hitting that goal? And we'd gather that data. So even though the actual value would change from part to part, we'd say, well, did you hit the goal you were after? Let's keep track of that. Sometimes we were a little large and sometimes we were a little small, but we could plot that data. And if it started to approximate that, nice bell-shaped curve, we could make some predictions about what that lathe could do. Now, by the way, if it was jumping all over the place, that usually told us there were some issues. There were some assignable causes that we need to work on, part of the setup, the tool holder, maybe bad bearings. We need to look at those. But as processes settle down and they start to approximate our nice bell-shaped curve, we can find an average here. And with a $15 calculator, we can find out where our curve goes from concave down in here to convex. There's a point of inflection right here, which it turns out is called your standard deviation, or sigma. I don't know how many of you were taught it that way, but I was talking to a statistician at a master's degree, and I said, yeah, it's where the curve goes from concave to convex. He said, oh, I know the formula for standard deviation. I just never knew that's where it was. Anyway, in a process then, we can find that inflection point once we've gathered some data. If we're at plus or minus 1 standard deviation, what you have in here is about 68% of the population. If you come out to 2 standard deviations, now it's about 95% of the population. If I come out to 3 standard deviations, now I'm at 99.73% of the population. And we used to consider that good. That meant you were only making, about 3 bad parts out of 1,000 back in the day. Now we like to talk about defects per million rather than defects per 1,000. Kind of keep these numbers in mind, though, as we move ahead here today. So let's say that somebody were to give me a tolerance that was plus or minus 1 standard deviation, and I knew I was going to make the parts on that engine lathe. Can I make parts? Can I hold them to that tolerance? Well, yeah, 68% of the time if we can keep our process centered on the goal. And you can't always do that because of tool wear and machines heat up and cool down and so forth. And sometimes with a less capable machine, you have a wider distribution here, so your sigma is a bigger value to include 68% of the parts that will come off that. And if I set a tolerance at plus or minus 2 sigma, 2 standard deviations, once again, if I could keep the process centered, 95% of the parts would be in tolerance. And here's our defects out here. If I put a tolerance of plus or minus 3 standard deviations, whatever that number is, then if I could keep the process centered, which you can't, that represents 99.73% of the stuff. And this is what we used to call a good quality level. That was before our friends over in the Orient were kicking our tail. Now what we want to do is calculate a CP, and all that is your design spec width, which is your tolerance, divided by 99.73% of the stuff if it was centered. This is historically how we calculate CP, dividing by 6 standard deviations. So quality often looks at CP. Production has some control over this standard deviation, how big that'll be. And design has control over that spec width because they're setting the tolerances or spec width in their design. They come up with a more robust design, they can give you a bigger tolerance. So hope everybody's okay with CP here. One way of looking at this I kind of like is imagine that I was shooting at a target. Maybe this is my target where the 2 lines cross. And here's some of my shots. So as you look at that, how would you describe what you're seeing here? Well, usually what people say is, well, you've got a good group. That's a good grouping right there. And I often respond, really? Doesn't depend on what I want to hit. Yeah, if I'm trying to pick off the woodchucks out in the field, I guess that's a pretty good group. But if my goal is to pick off the head of a match, that's not so good. So what CP is doing is it's comparing your dispersion, which is this group up here, you're seeing most of it, to what you're trying to hit. But another thing we need to worry about is how accurate am I? So one more time with CP. It's looking at the size of the target, or the tolerance we could say, and dividing by most of the dispersions. Remember that was 99.73% of what we could do, or 6 standard deviations. But I worry more about CPK. And CPK is not Cabbage Patch Kids. My wife kept hearing me talk about CPK, and one Christmas she saw this in the toy store and gave it to me as a present. She knew I'd love it. But no, that's not what we're talking about. An analogy I use for CPK is, imagine that there's a 4 by 8 foot sheet of plywood on the floor in the room where you are. Question for you, could everybody cross that 4 by 8 sheet of plywood without falling off the sides? My guess is you probably could. And you could probably even do it backwards, maybe, I don't know, some fancy moonwalk or something. Well, I want you to think about the width of this 4 by 8 sheet of plywood as your spec width. And I'm going to use these 4 by 8 sheets of plywood on a bridge, crossing over a gorge. It's 1,000 feet to the rocks below. And I just want to ask you, how many of you are going to cross this bridge doing a moonwalk backwards? My guess is not too many, especially if there's no handrails.
Yeah, no one's raising their hand for this one, so I'm thinking.
Oh,
yeah.
Yeah. Well, if they're going to cross, they're probably going to do it on their hands and knees. And they're going to say, I've got to stay away from that edge, got to stay away from that edge. Well, that's what CPK does. It doesn't look at how close you are to the center. It looks at how close you are to the edges and says, I have to stay away from that edge and this edge. And I'll tell you what just came to mind. We're still having winter up here. There were some snowflakes in the air last night up in upstate New York. But just a week ago, we were driving home from a little gathering, and my wife was driving, and we couldn't see the road. We'd had a couple inches of snow, and it was kind of slippery, and I could kind of sense when she was on the edge of the road. I'd say, no, you're too close to this side. And she'd go over. She was aiming for the middle, really, but what she was really doing was staying away from the edges. Now with this fellow that just went across here, I'll bet if I tied a piece of chalk onto his tail, I would have gotten a white line right down through the middle of that bridge. Somebody not too long ago said, 1,000 foot to the rocks below, that line wouldn't be white. Well, we're not going to go there. We'll just let that slide. But think of this as an analogy for CPK. So I look at the average of my dispersion and see how close that is to the edge of the target. And by looking at that and getting that number, I can predict how many of my shots might go right off the target. And those would be out of spec, or those would be defects. So I can make that prediction. So your CPK calculation says get this distance, which is from your average, which is mu, and subtract that from your closest spec, which would be the edge out here, and then divide it by 3 standard deviations rather than 6, because I'm not so worried about this half of the distribution. That's going back where it ought to be, you know, toward the center. So now instead of 6 standard deviations, I'm only looking at roughly half of the distribution. That would be these guys right here. Okay, so how do we do this drawing preview? Well, we said first we gather the voice of the customer. Let me give you an example. Let's say the customer says, look, I have this airline. It has 80 pounds per square inch in it. I want some device that will move 1.5 inches. I want it to push with 400 pounds of force. Here's how I want to mount it. And it has to survive 1,000,000 cycles. So this is what we call voice of customer. Now here's the old experienced designer or engineer saying, well, how would I do that? Pneumatic piston would work, and there's lots of choices with a pneumatic piston. I could go with no seals. If I held the tolerances tight enough, there'd be a little leakage, but it'd work. We used to build little air engines at the college with no seals. You actually floated on a little air, like an air bearing. I could have lip seals, I could have O-ring seals, oh, the list just goes on. Or maybe instead of doing that, I could have a little air motor. And that little air motor I could have with a gear train, and it could move back and forth. Or maybe I use a diaphragm of some sort that I can add air pressure to. So there's lots of alternatives here. Now, maybe my paradigm is pneumatic pistons. So, okay, I'm going to come up with this piston. And this is kind of a schematic of it here. But one of the critical areas for this piston, if I can get it to move, there we go, is here between the piston and the cylinder. And I've gone with no seals. I'm going to let a little air leak, but it's going to be a cushion of air, so this will slide very nicely. Well, in order for this to work and work well, I've determined that on the diameter here, I need to hold a tolerance of plus or minus 0.005 millimeters, pretty darn tight, or a total of 0.01 millimeters. What's that, about 4/10,000ths of an inch? That's also plus or minus 1 standard deviation if I'm going to make these parts on my turret lathe. I know where we're producing them. So if I look at CP for this design, my spec width is 0.01, and 6 times my standard deviation on my turret lathe is 6 times 0.005, because 0.005 was my sigma for the turret lathe. So if I do the math, it turns out my CP is 0.33. Now that is a CP of 1. I've really put the tolerance here at plus or minus 1 standard deviation. Can I make these pistons? Yeah, 68% of the time, if I keep the process centered. Now, some of them will be oversized, right? About 16% will be oversized. Those are the reworks, see? And 16% will be undersized, and those are the scrap. And some companies produce things like this. So my question to you is, let's say you're a manager over this designer. And the designer says, boss, I came up with this great design. We don't have to use any seals. It's going to be terrific. I have to hold these tolerances. We looked at CP based on the equipment that we have, and it's 0.33. What should you do? Well, if you're the manager, you should take this designer's drawings and roll them up like a newspaper and whack them with it and say, get back to that CAD system until you can come up with a more robust design. This isn't very robust. So you go crawling back to your CAD system and say, okay, well, I could put some O-rings in there. And purchasing got involved, by the way. There's little O-rings, little cross sections, and they're kind of cheap. And then there's fat O-rings, but there's more material in them. They cost more. And purchasing says, yeah, let's go with the little O-rings. And according to the catalog, it says that I have to hold a size tolerance of plus or minus 0.1. Or that's a total spec width of 0.2. I divide that by 6 times the standard deviation of my engine lathe, and I get a CP of 0.67. So in other words, I put my tolerance at plus or minus 2 standard deviations. That means 95% of the stuff would fall in here if I could keep the process centered. 2.5% would be oversized. That's rework. 2.5% would be scrap. I can predict this from here. So you're the manager. Boss, I came up with this new design. The CP is 0.67. What should you do this time with the drawings? Roll them up like a newspaper and whack that designer and say, get back to that CAD system until you come up with something more robust. Well, to have something more robust, I might have to go with fatter, squishier O-rings. So I have to work with purchasing a little bit on this. They won't be happy. Turns out, though, that according to the catalog, now I can have a tolerance of plus or minus 0.015, a total spec width of 0.03. My CP is 1. So remember, CP of 1, that would be like plus or minus 3 sigma. 99.73% of the stuff would be in spec if I could keep it centered, which you can't. So yeah, I'll have a few that are oversized and a few that are undersized. I'll have too much air leaking by. This used to be considered good quality, especially in the United States, a CP of 1. You're the manager. What do? Hopefully you take the drawings, roll them up, hit them like it was a newspaper, and send them back again. We need something more robust than this to reach today's quality requirements. Because the one thing that we kind of left out here is I can't keep a process centered. Tools wear. Machines heat up and cool down. This floats around. As it drifts a bit, I get more defects out here. And that's where CPK comes in, because CPK looked at this average right here and looked at how close you are to that limit and compared it to 3 standard deviations. And when I do that, I can then tell you what % of parts are going to be out here oversized. So for our turret lathe, if we were going to design at 6 sigma quality, that's plus or minus 6 sigma for your tolerance, which would be, let's see, what do we got here? If the tolerance had been specified at 0.03, that's 6 times the standard deviation. And the mean of the process was not allowed to shift too much, more than 1.5 sigma, which is kind of a manufacturing standard these days. Then my CPK would be 1.5, and that would mean that the probability of making defects out here would be about 3.4 per million. That's how Motorola defines 6 sigma quality. 3.4 defects per million is considered a 6 sigma design. Okay, I want to take you through a little case study here as we're getting nearer to the end of the brown bag. When do we do our design preview? Right here. There's no drawings yet. I've made the solid models. It looks like it'll work. This is a plunger that moves back and forth. I think I have an animation of that. Ideally, you take it a step further. For about $2,500, you can buy a little rapid prototype machine and get the parts. They won't really work, but have the parts in your hand. So I strongly recommend that. As I've gone through these design previews, when we can hold something and discuss what surface is touching what other surface, it's really helpful. And we apply the GD&T. And GD&T, I like to say, is as easy as 1, 2, 3, and sometimes 4. First thing we do is establish datums for dimensional origin. There was one company I was doing several design previews with, and after we did a couple of them, I said, you know, you really don't need me here. You know what to do. You know the steps. And they said, well, Don, we want you to come in because you give us confidence. And I can remember the next meeting I went in on, the leader said, okay, where do we start? And he looked over at me, and I kind of raised my eyebrows, and he said, should we pick out our datum features to establish datums? And I just nodded my head. And then put controls on those datum features, and he knew to do that. And then you need to locate other features on the parts from these dimensional origins established by your datum features, your datum reference framework. And then only if necessary do you refine with auxiliary datum reference frames. I'll show you one example of that, and with other geometric controls. This really follows our hierarchy, our GD&T hierarchy pyramid. I'm sure all of you have downloaded the 3D model that you can cut out and fold up, and probably have it sitting right there on your desk. But as this pyramid says, first we start by identifying our datum features, and we put controls on those datum features. They're not datums, they're features on the part that need geometric controls. And then you locate everybody else. Now all features have surfaces. There's only one geometric tolerance that can locate surfaces, and that's profile of a surface. So many companies are now making this their general tolerance, as big a profile as they can stand, because that can control where everything is. We do have the special case, though, of features that are known as features of size, and there's rules about what size does. And we can locate features of size with not only profile, but we can locate those with position and the runouts if you're dealing with lathe type parts. So this kind of guides you into step 3, how you locate your features. And then only if necessary do you come down into this region down here with refinements of orientation and form depending on the type of features you're dealing with. For instance, for planes, these are the 5 that I'd consider. So first we locate them, because this profile controls all of this, all that you see here. But you might need parallelism that's better. You might need better flatness. So you'd add a refinement at that point. So we assign tolerances, and then we analyze them. So you allocate, and then you analyze. And once you've analyzed, you'll probably have to go back and reallocate. Deming said you go through this several times, allocating and analyzing your tolerances.
Don?
So let's just take a look at this fuel valve now. Yeah.
We have a question. I'm just trying to hang on one second. Question from John Hawk. Hang on one second. Let me unmute him so that he can talk. Hey, John.
Yeah, I'm sorry. I was just being nice. I said, yes, I have it. It's folded up on my desk.
Oh, the pyramid. He has the pyramid. Well, thank you. It's nice to hear another voice during the course of this thing, so thank you.
You're welcome.
Well, John's a real friend of ours. In fact, just 2 days ago, I was admiring some wooden models that he made and handed to me that I need to do some work with.
Enjoy.
So good to hear your voice, John. Okay. All right. So let's kind of walk through this. Here's a cross section through this fuel valve, and just so you know how it works, this yellow part here is a bobbin. And you wrap wire around it. It's really creating a solenoid. You have an iron core that's molded into the bobbin. And if you remember back in general science, you probably took some wire and wound it around a nail and hooked it up to a battery and turned it into a pretty strong magnet. Well, that's what we're doing here with this iron core and the winding around the bobbin. So the way this thing works, we have a plunger that moves back and forth. There's a spring. The spring will move the plunger to the left. This is a rubber plug as part of this plunger that shuts off the fuel right here. When I energize the solenoid, the plunger moves to the right, compresses the spring.
What am I doing?
And it opens up and fuel can flow.
To Dad's.
So here's an animation of how this then works. So to allocate the tolerances, I'm doing my best, taking my best guess at what tolerances I put on these critical dimensions, these critical distances. And then I would do an analysis, in other words, a tolerance analysis, to see if I'm maintaining the gap that I need to. The critical gap right here is between that rubber plunger and this fuel block. If it's too small of a gap, I won't get enough fuel flowing. If it's too large of a gap, when it slams shut, it's going to shorten the life of this plunger. So the critical dimension and tolerance is right here. Well, how do I hold that tolerance? Well, what I do is I have to take this tolerance and budget it. Take that 0.2 and allocate it out to the parts that are involved in this loop right here between the block or fuel block and the plunger. So I did the best I could here with that. And here's my tolerance analysis. These become vectors. Some are positive going to the right, some are negative going to the left. And in order to get a gap of 0.8 plus or minus 0.2, worst case, here's how I had to allocate the tolerances, you see. So I'll come back to that tolerance analysis in just a few minutes. But let's talk about these steps here. Selecting datum features. I mentioned there's been 10 of these brown bags. One of them was, how do you select datum features? Based primarily on function, is where you start, but sometimes you have to use processing datums, datum features. And sometimes with things like sheet metal parts and plastic parts, you need to add restraint notes that tell how to hold the part to your datum feature simulators. Just a word about those temporary datum features. This is what the standard says about these temporary datum features. They're in-process parts, such as castings, forgings, machinings, or fabrications. So I may have these temporary datum features that don't have anything really to do with function, but I use them then to create permanent functional datum features. And they go on to say that these temporary datum features may or may not subsequently be removed by machining. My recommendation is you never remove them. So looking at the fuel block casting, and that's what we're seeing right here, we added some features and we recessed them so that they never have to be machined away, because then you lose your track record. So you notice I have a little notch here, one here, and one here. Why are those notches there? Because I want to grab this in a 3-jaw chuck. So on the raw casting, if you think about what's the function of a casting? Well, its function is to machine clean. So when I machine it, I machine the functional features on it. I want to make sure there's enough material there, but not too much. And I'm going to grab it in this 3-jaw chuck. Now, how do I know all this? Production was sitting in the design preview. And as we're talking about how to make this fuel valve, they're thinking about the machine they're going to put it on to do their machining of the casting. These surfaces right here on this 3-jaw chuck became my primary datum feature that you'll see in just a second. We'll go back to it. And then the diameter that's grabbed by these 3 jaws became secondary. And then I used one of the notches to drive or orient the part. So we thought about how does the part go into the 3-jaw chuck. And it sits on those jaws on these 3 surfaces right here. So we call those datum features Z. Notice there's 3 of them. The profile says I'd like them to lie in the same plane. So you can see them down here in this view. They have nothing to do with the function of the part, but they have everything to do with the function of the casting to machine clean. Y is 3 surfaces again, and it's these 3 surfaces that I'm going to close in on with the 3 jaws of the chuck. And then X is this slot that's opposite this boss right here where we're going to do some machining. And so this I'm using to orient the casting. So I've identified my datum features, Z, Y, and X. I've put geometric controls on them, profile here, profile there, because I'm controlling the surfaces, and position on the width of those 3 notches. But I have to now look at the function also on this. And the functional features are the mounting feature here that gets machined off in the casting. This diameter right here is functional. This surface is very functional where the body comes in contact with the fuel block. And I have to pay attention to this especially because it's part of my vector loop for this critical gap that I have.
Jeff, you have a question? Go ahead.
So, yeah.
Earlier, can you hear me?
Yep.
Mm-hmm.
If you go back a couple of slides, this is an interesting subject on the position that you had on the 3 tangs, or the 3 slots there. The 3 times 6 plus or minus 0.5. I noticed there to Z and Y. Now that looks like it could
That's
go
correct.
in a different orientation. I noticed you have an X down below. Should the position of those things be controlled, or should that last degree of freedom be controlled, the rotation?
Well, this
reposition.
position is controlling all 3 notches. So
Right.
it's controlling them with respect to each other and with respect to ZY. But everything else on this fuel block will be controlled to X, ZYX. And you can see down here in the general notes, you see the
Right.
profile of 2 millimeters to ZYX?
Got it.
So we're okay now? So things like this boss right here is located with respect to ZY and X.
Got it. Yep, that's what I was going after. Is I just wanted to make sure I understood that the clock
Excellent.
is taken out. Thank you.
You've got it. Okay, great. So now as I look at the machined fuel block, this is how it mounts on the engine. And so that's a primary datum feature. And it gets centered on this diameter, so that became my datum feature B. But I had to locate these machined features on the casting. So you notice that A is located with a profile to ZYX. There's our cast datums that remain. They're still here. You can see them over here in this view. We still have them, so we have a track record. And I'm going to center up this feature to ZYX, and then it becomes datum feature B, and it was optional, but I tightened up its perpendicularity to the plane established by A. And this flatness here was optional. It was a refinement. The profile gave me a flat within 0.4, and I asked the question, is that good enough, or do I need this flatter? If that's a sealing surface right there, I maybe need to tighten up the flatness. Now, as you look over here, this surface is where that body mounts. It's kind of a loose thread that they have there, and when you tighten up the thread, you make full contact on this surface. So I've located it from A, but I've made it datum feature D. And then I'm controlling this critical distance right here, this 12, where the plunger contacts with a profile of 0.1 back to D. And so I won't walk through this whole thing, but I hope you get the idea then, that I have those cast datums, establishing functional datums, and even some more auxiliary datums where I need to make this all work. So from there, then, here's my fuel block. Here's that critical distance I just pointed out. Here's where the plunger contacts, and here's datum feature D. And this is where I hand off to the body. Now the body critical dimension is this 3, because that's where it hands off to the bobbin. And then within the bobbin, I have to locate this iron core. That distance has a tolerance. And in the iron core, from there to this spot that locates this plunger, I have a critical dimension. And then actually through the, there's a sleeve on here of 0.2 millimeters. And so that's a critical dimension. And then, let's see, there's one more here someplace. Right here, the 28 is on this plunger going to the end of the rubber stopper. So there's kind of my vector loop. And I had to guess at assigning these tolerances. We're getting short on time, so I'm going to go through this kind of fast I kind of guessed at these tolerances for these critical distances. Well, then I went into this database. This is that tolerance capability expert I mentioned. And the body was an impact extrusion. So I went to that particular database. There's a lot you can choose from here. I don't know if you can read them, but that's hot forging and casting and sheet metal working down here and cold drawing, extrusions and machining processes and so on. But if I put in the distance, in this case it was that dimension of 3, and the tolerance I'm trying to hold, which was a profile of 0.4, so I put that stuff in here and it predicts for me a CPK. And by the way, it predicts a pretty bad CPK. So we did that with each one of these parts. And so I'm just going to go through this quickly. Hope you get the idea. So I'm going to get to the conclusion here. This was more like a 3 sigma design, it turned out. And a study from Motorola University found that if you design at 3 sigma, about 1/3 of your resources go into rework, repair, and analysis. If you design at 6 sigma, only about 1% of your resources go into rework, repair, and analysis. So we really wanted this to be closer to a 6 sigma design. So when we analyzed all this and we looked at the CPKs, here's what the company was shooting for with CPKs. These are corporate goals or targets, 1.38. But looking at the database, on the bobbin, my CPK was 0.5. Well, that's not good at all. What am I going to do here? Well, I'm going to have to redesign that. And the body was the same thing, and here and here. Now on the tube, I had a fantastic CPK. What did that tell me? I gave that tube way more tolerance than I needed to. And so I can rob some of this tolerance and distribute it out to these parts to get better CPKs. So here I was very capable. Now remember I told you that when you look at the CPKs you can predict the defect levels. Well, they did that at this company, and they predicted that very, very high volume of fuel valves they were producing in the automotive industry, they were predicting a failure cost of $6 million per year if they went ahead with this design. And they said, that's no good at all. So what do? When you're not meeting your corporate goal, you have to come back here and get a new flash of inspiration. And that's exactly what they did. I want to point out, this is that iron core that I showed you. They made it larger, and they milled these grooves in here. And the reason for that was so the plastic could flow through those grooves, and actually some of the iron core could stick outside the bobbin. Originally, the bobbin contacted the body on this shoulder. The redesign, the iron core contacted the body, and the bobbin would just float. Well, what that did was take the bobbin out of the tolerance accumulation, out of the tolerance loop. There were 2 vectors here, one to the bobbin and one to the core, but now I could go right to where I contact the iron core by making that change. So that changed this vector diagram. And if we spend a moment looking at it, we'd see there's one less vector here. And we did the analysis. And we robbed some of the tolerance from the tube because, remember, it had more tolerance than it needed. So here was the result. The bobbin was no longer in the tolerance stack. So this was capable, this was capable, this was, and this was. We met our required CPKs and then some. And the predicted failure cost per year went from $6 million per year to $6,000 per year. Pretty impressive. So the results of using design previews, as I've just shown you, will give you a more robust design that's insensitive to variation, higher quality, shorter time to market because you're not out there doing a lot of troubleshooting. You'll have a better understanding of your product and what you're capable of. And your analysis will give you fewer fit and functional problems and fewer engineering changes, which we all know costs us money. So that's what I wanted to say about drawing previews. and our time is just about up, but I would like to entertain any questions that there might be.
Go ahead, Chris.
Wendy, are you there?
I am. Hello? I'm here. Can you hear me? Yes.
Chris has a question.
Chris has a question. Let me see here. I think I need to, oh, he doesn't have a mic. Hang on. Let me make my question window bigger. Don, when controlling a feature at 0 max material condition, do you feel that it has an impact of the machinist moving away from the target goal to the side which gives the maximum advantage of tolerance and therefore affecting your process?
Well, that's a great question. And I guess you could ask that same question anytime you use the maximum material or least material modifiers. Because if they understand it, they know that if you put an M in a circle in that tolerance, if you work closer to least material condition, you'll get more tolerance. And that's where CPK comes in. CPK says, no, stay away from the edges. So to try and answer your question maybe a little bit better, when we look at a 0 at maximum material condition, if I do a dynamic tolerancing diagram, and I put size here, and let's say it's on a hole, then maximum material condition is here, and we'd say you get 0 position tolerance, but as you make the hole bigger, then you get more tolerance. And so your question is, will the machinist tend to work closer to here? Well, if I have a required CPK for that production area, it's saying stay away from the edges. Your distribution is to stay away from that edge right there. What it does do with 0 at MMC is it gives them more range to float in here, and so it'll give you a less expensive part in general. So I hope that answered the question.
Chris? I think it might have. Okay. Swapnil, you have a question? I unmuted you.
Yeah.
Go ahead.
Don, this is Swapnil from India. You mentioned this tolerance capability experts that software or module you showed. How reliable it is, like, when I think in terms of, say, some kind of machining process or some kind of molding. So do you really rely on those values as a starting point and they're fair enough? I know, like, they cannot be 100% accurate, but what is your guess for that? Because that is really impressive. It's like, many times designer face that problem, where to start.
Yes, that's right. That's right. And that's a great question. I'm getting a lot of feedback, Wendy. Could you mute him again while I answer?
There we go. Go ahead.
Okay. A couple of things. One, you want that data to be evergreen. Now, the particular program I mentioned, Tolerance Capability Expert, the data was gathered by a lot of research students at the university. It's based on a lot of ISO studies, a lot of studies in Europe, and based on best practices. And the folks that put it together claim a very high correlation between what they predict and what actually happens when you make the parts. They do keep it evergreen. So you subscribe to this software and they update it as more information becomes available. I hope that answered that one.
Swapnil, did it?
Yeah, thanks for that, Don. And this is like, we can subscribe this or purchase this, like this software, or how it works daily?
Well, you can contact a company called Capra and subscribe.
Let them know we sent you.
Capra. We distribute. I'm sorry?
I said let them know we
yes, tell
sent
them that
you.
we sent you, please. we distribute the software in North America, and I don't mean for this to be a big commercial, but I discarded that. Let me see if I can just quickly pull that up for you so you can have an idea of how it works. It's Capra Technologies is the company, and I hope this shows up big enough on your screen in a moment. I have to get Wendy to buy me a new computer. This one's very slow.
It's on its way. While you're doing that,
it's not coming up.
While you're doing that, John Hawk says, from Chris's question, sometimes we want to stay close to one edge as we use unequal profile tolerance zone. And we use unequal profile tolerance zone.
Yeah, I'm afraid to answer that one. I'll tell you why. There's a debate that's actually been going on in the Y14.5 committee about things like unequal tolerance zones. And I have an older version of the software on this old tablet, and it's not loading. So I'm going to go back to my PowerPoint and answer the next question. I'm sorry, I couldn't demonstrate it.
Oh, that's okay. Swapnil, if you want to, hang on one second there, Don. Swapnil, if you want a demo or if anybody wants a demo, send me an email and I'd be happy to give you the information so that you can get a demo and more information about the software.
Let's say this is datum feature A and I make this, I don't know, 20 millimeters. But then on the surface, I give you a profile of, we'll say 4 millimeters, circle U, 1 millimeter to A. So what that's saying is you can go out a millimeter from basic, and you can go in 3 millimeters from basic. And the question that came up, the debate we had, is will manufacturing work closer to the 20 because we use this unequal bilateral tolerance? And it hasn't really been settled, but there's nothing in the standard that says that's what you're supposed to do. And once again, think of this tolerance as crossing the bridge. If you have CPK requirements, you need to stay away from this edge and this edge, which is going to mean that the goal is here at something like, what, 19.8, even though it says 20 basic. There's nothing in the standard that says you have to work closer to the 20. Now, there may be a new tool, there might be a new modifier coming out that'll change that. But as of right now, you have to look at how the shop is rewarded. Did that answer the question?
Thank you.
Yep, I guess so.
Okay, good.
Thanks, John.
Yes, thank you.
Any more? I know we're about 10 minutes over right now. Let me just say that you're all welcome to email me, Don at Tec-Ease, with other questions, follow-on questions, anything you saw here. .com. This is recorded, and so you can go back and play it again if there's something you might have missed.
Yeah.
And I'm going to say, please, 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 if you have ideas for brown bags, if there's something you'd like me to talk about, we had a couple of questions about zero at max material condition. Maybe I should do something on that as a brown bag. You know, that would be great. So just let me know what you'd like to see, and I'll do my best to provide it.
Couple just comments. Frank Roderick says, that was absolutely phenomenal. These brown bag sessions are always informative, but holy cow, this was the best session yet. I definitely want to digest the material, and on that note, everyone, please remember these are recorded and will be posted on the premium site, so if you want to rewatch it, feel free to do that. And Swapnil says, thank you, Don and Wendy, appreciate it. It was a really helpful brown bag. Enjoy and learn new things. And we're getting lots of great presentations.
And to Frank.
Yep.
Okay. I was just going to say to Frank, okay, Frank, next time I see you, I'll buy the beer.
Oh, he said he was going to buy you dinner, so there you go.
Oh, okay. All right.
Chris.
Well, that was very kind of you, Frank. Frank, if I can, a little plug here. Frank has worked for a long time with NASA, and flattered to get a comment like that from Frank. Thank you, sir.
Chris Scherkel says, thanks, Don. Great job. Dennis Schwartz, great presentation. And Juan Lai says, great job. Enjoyed the presentation. We enjoyed having all of you here. Let's see. Tungton says, thank you, Don and Wendy. Another excellent topic. Looking forward to the next one. Thanks, everybody. It doesn't look like there's any more questions, so we will say goodbye. And we look forward to seeing you guys at the next brown bag session.
Okay, great. Thanks so much. And thanks, Wendy, for facilitating this.
Of course. Bye-bye.